I'll like to go ahead and get started talking about graph frames, which are data frame-based graphs for Apache Spark. Really excited about this. It's the first talk I've given on this new Spark package. Just quickly about me. I work on Apache Spark as an MLlib maintainer, and I'm a software engineer at Databricks. My background is in machine learning, and one interesting thing, part of what I researched then were probabilistic graphical models, which are graph representations of probability distributions. So this is a topic very near and dear to my heart. The one requisite slide on where I'm coming from in terms of the company, I'm from Databricks, which is the company behind Apache Spark. It was founded by the creators of Spark in 2013. We've continued to contribute a lot to Spark, including, for example, in 2014, about 75% of the code. And basically, it's a hosted Spark platform designed to make working with big data simple. Cool, but here's the main stuff that I'd like to talk with you about. First, I'll introduce graphs, and by introducing the main concepts behind graphs, we'll introduce the running example I'll use during this talk. I'll also mention some graph frame basics, how you create it, what it looks like, then go into queries and graph algorithms that you can run on graph frames. And then I'll take a step back and try to phrase graph frames in terms of other libraries, how it compares to GraphX, and so on. For experts and power users at the end, I'll mention how you can write custom algorithms, and finally, future plans. Cool, so what are graphs? Well, the running example I'll use is airports and flights between them. So here's a very simplified graph of airports in the United States. And you can see that each vertex is some airport. For example, this one is JFK. Every edge between airports represents some path between two airports. For example, you can take a flight directly from JFK to Seattle. And also importantly, we can associate data with the various vertices and edges. For example, JFK might have other data such as city, New York, and state New York associated with it. An edge might be associated in our example data set with a particular trip or flight. In this case, from JFK to Seattle, with maybe a delay of 45 minutes and some trip ID assigned to it. So you can see how it creates a very nice intuitive structure, both for people to think about and for algorithms to structure computation and communication. Now, graph frames are phrased in basically the way you would expect. You have two data frames, one for vertices, one for edges. So the vertices data frame has one vertex or airport per row. And you note that there's a special column, ID, which is a column with a unique ID for that vertex. You can see JFK in that, Seattle, and so on. And every row will be a different airport in our data set. The edges data frame is analogous with one edge per row, but now with special columns, source and destination, which use the IDs from the vertex data frame. You can see we have other metadata associated with each of these edges. This is also, if you're used to GraphX, sometimes referred to as vertex or edge attributes or vertex or edge properties. Cool, so this is what a graph frame looks like. And I'd like to just quickly jump into a notebook where I have set up here. Let me zoom in. And please say if you can't read it in the back. But essentially, this is a notebook. It is using Databricks notebooks, but this is code which will be, or actually already is available online, and is runnable in any Spark installation. So what I'm doing here is just running some code to load in data frames. And then after it loads, I'm going to display those data frames. And I'll note that this is just a microcluster of 8 gigabytes of memory or something. But it will allow us to analyze a decent-sized data set for this demo. So after this has loaded, then we can say display the airport's data frame. And you can see this is going to be our vertex data frame. It has a unique ID column and other metadata, city, state, country. We could also say display this other data frame, departure delays geo. And this is going to be our edge data frame. You can see we have a source and destination column over here. And the other columns are metadata about each of those strips in our data set. Cool, so given these data frames, we can now create a graph frame. That's pretty simple. Basically, you import the graph frames package, and then you construct a graph frame by passing it those 2 data frames for vertices and edges. Currently, the graph frame is basically just storing those 2 data frames. If you call vertices and edges, these are just, data frames with the columns that we would expect. So it's really simple to create graph frames. Now, before I go into queries in the notebook, whoa, that's interesting. I'd like to sort of cover them at a higher level. I'm going to divide queries you can make on this graph frame into 3 sets. First, what I'll call simple queries. Next, motif finding. And finally, graph algorithms of the type you may find in, say, GraphX. So what are simple queries? By that, I mean, first, the vertex and edges are represented in data frames. So you can make SQL or data frame queries on them. And we'll see you can answer things like, what trips are most likely to have significant delays? The other type of simple queries, I'll say, are graph queries, such as looking at vertex degrees, in other words, the number of edges incident on a vertex, or say triplets, which is a simple join between vertices and edges in order to get, for each edge, not just the edge data, but the associated source and destination data. Cool, so just to see what this looks like. Yes, question.
Data frames seem like, I'm new to this, so here's my dumb question. It seems like it's a relational chain. Why do you call it a data?
I wasn't involved with the original phrase data frame from, say, R or other libraries. But I do think it's become a very useful concept in terms of, sure, having tables where in addition to it being a table, you have certain expected operations, for example, aggregations, et cetera, that you can do, and a particular API for it. But yeah. We can discuss it offline too. Cool, so after importing some SQL functions, what I'm gonna do is first say, how many airports and trips do we have in the data set? Of course, that is going to be a very simple query on the data frames, just counting. You can see we have 279 airports, about 1.3 million flights. Could also ask, as I said before, what trips are likely to have significant delays? Now, all that question is, let me zoom in more, is asking, take the edges data frame, group into unique paths, source to destination, take the average delay, and let's sort by it so that we see the really significant ones. You can see if you're going from JFK to, I think that's Jackson Hole, might have a very high delay, and so on. But you get the idea. You can make very expressive queries just on those data frames. You could also say, ask, what destinations may often have delays if you're flying from Seattle? And there again, it's a simple filter on the edges, where in this case, the darker states indicate that you may be delayed more, at least in this time frame, flying from Seattle. Cool. The other type of simple query I mentioned were vertex degrees. And that can answer some interesting questions very quickly, such as, say, what are important airports? In this case, you can see Atlanta has very high degree, in other words, many flights coming in and out of it, as you probably already knew. Cool. So in addition to these simple queries, one really cool thing, which is new in graph frames, which was not in GraphX, is motif finding. And what that does is let you search for structural patterns within a graph. So here I have the simplified graph of the US. And in order to explain motif finding, I'm just going to go through an example. So here we're looking to find this motif with 3 pieces. Look at the first line. It says we're going from a vertex A through some edge E1 to a vertex B. So for example, in this graph, something which matches is, say, Dulles is Washington Dulles Airport is vertex A. It connects to JFK Airport. The next line in our query says that same vertex B, JFK, connects to some other airport, C, in this case, Dallas-Fort Worth. And the final line in the query says there is no edge going back from C, Dallas-Fort Worth, to A, IAD. Cool. So we found this one example of a motif, or an example of this motif in the graph. And what you'll get is a data frame with a bunch of rows of a bunch of instances of these. After that, you can really tailor this query by filtering using vertex and edge data. For example, we might want to say filter based on that first flight, E1, having a delay greater than 20 minutes. So to see what that looks like, we're going to look at city and flight relationships through motif finding. And the question I'll ask is, what delays can we blame on SFO? And I'll give the caveat that to really blame SFO, you need to do a more thorough analysis, et cetera. But just for fun, we can look at motifs which go from A to B and B to C, where we're then filtering, saying that middle airport B is SFO. At least one of the flights was delayed significantly. And then finally, at the end of our filter, we're creating a relationship, or we're requiring this relationship between the 2 edges, saying that the first edge's trip ID is less than the second trip ID, which, because of what we know about this data, just means it came before that in time. So this is a very rough way to decide how to blame SFO, but it's fun to do. So what this is doing is essentially doing a set of joins running in the background, but can take advantage of predicate pushdown with this filtering. Now what we've gotten back is a row for every element, every possible match in our data set, in our graph. And each row is going to have the data associated with every element specified in our motif, vertices A, B, and C, and the 2 edges. Now I can see that the edges and the vertices still have that metadata associated with them. You know, edge E1 has the trip ID, the date, et cetera. Vertex A has the ID, city, state, country, and so on. You can imagine creating very powerful queries this way. Cool. All right, so that's motif finding. The final type of query I want to mention are graph algorithms. I've divided it into sort of 4 groups. The first is finding important queries, where of course the natural answer is PageRank. We can also search for paths between sets of vertices, breadth first search, shortest paths, algorithms like that. We may also be interested in finding groups of vertices, whether that be components or communities. There's several algorithms available. And then there are also a few other algorithms which are a bit more esoteric graph-specific algorithms like counting triangles or this recommendation algorithm. Cool. So I will mention that all of these except breadth first search are sort of the key algorithms offered by GraphX, and that we've taken advantage of that really by having most of these implemented currently by wrapping GraphX. There are a few algorithms, breadth first search and triangle count, which we implemented using data frames, but the others are wrappers. And the cool thing about this is this made us think a lot about how to interoperate between the 2 libraries. So if you have existing work in GraphX, we have some functionality which should help you be able to interoperate. Now just to show the API for running these algorithms, let me come back to the notebook. and look at airport importance. So you can see what this query looks like is taking our trip graph, calling a function PageRank, where we can pass named parameters. Of course, this is in Python. In Scala, it forms more, or in Java, it has more of a builder pattern. But in this case, we follow Python syntax using named parameters, here passing the max number of iterations. And that returns a graph frame augmented with new columns of PageRank. So we can look at the vertex column, the vertex data frame, say sort by the different PageRanks, and display it, limiting it to the top 10 airports to try to find sort of a different view on airport importance. So what this is doing is converting to a GraphX graph, running in GraphX and converting back. So it's approximately as scalable as GraphX, but has a conversion overhead. Eventually, it will be cool to port more algorithms to operate fully in data frames. But this was a great way to immediately support everything which is in GraphX. And as you might expect, Atlanta comes up with a very high PageRank, followed by Dallas, Chicago, and so on. So this is a abbreviated version, actually, of a longer notebook, which is available online. So I'm just going to mention that at the end of my slides, there will be a link to a blog post, which will have this notebook, which has a much more detailed analysis demoing graph frames. Pretty cool to check out, including some neat visualizations looking at, say, connections between different airports in the US.
Can I ask you one more question?
Is there a question?
Did you query an RDD?
Right, so to run PageRank, yeah, that was converting the graph frame to a GraphX graph, which is, yeah, a pair of RDDs, and running the algorithm there and then converting back. So yeah, that's kind of the functionality in terms of queries and algorithms. I will mention one really nice thing about using data frames, which is to make saving and loading graphs so much easier. Essentially, our answer right now is you save and load the data frames. A graph is a pair of data frames, so you can use all of the, the full SQL data source functionality to say read from Parquet, write to Parquet, etc. That said, it will be nice in the future to add more data sources for some graph-specific formats, as well as maybe mimicking the data frame API, where here we're having to call read and write twice, once for vertices and once for edges. It'd be nice to make it a single call. Another really nice thing about using data frames is it made it very simple to offer a very uniform API between Scala, Java, and Python. And this is exciting to me because it's the first time that Java and Python have really had access to the GraphX functionality. I will say there are two missing items if you're about to rush out there and test it. Java friendliness has not been tested well. It should work, famous last words, but we're still in the process of adding proper testing for it. The other APIs have been tested. Python also does not have aggregate messages, which is a primitive for writing custom algorithms, but that will be added. Cool, so now I'd like to step back and sort of look at this in light of other graph libraries. They're kind of divided here on this slide into two sets. One for graph algorithms, which I think of as sort of standard and custom algorithms optimized for batch processing, iterative, sort of expensive things to run. And GraphX I would group in this category. There are also a number of libraries built for graph queries, which I think of as like Motif Finding, maybe point queries about specific vertices or edges, and also updates. So graph frames, I think, is a first step towards supporting both of these use cases within Spark. We definitely have support for the graph algorithm side. We have support for running graph queries like Motif Finding, but I will say we currently don't have a good way to do point updates. Right now, the way to do point updates would really be to update the underlying data frame, create a new graph frame with it. So relative to GraphX, we tried to basically keep it very analogous. GraphX is built on RDDs, graph frames on data frames. Graph frames adds some language support, as well as support for queries and other use cases. Vertex IDs are an interesting case where GraphX required that vertex IDs be long types, whereas in graph frames, you can basically have that vertex column, vertex ID column be of any catalyst type. Vertex and edge attributes in GraphX are basically some arbitrary type associated with a vertex or edge. In graph frames, basically any extra columns in your data frames become vertex or edge attributes. And finally, the return types are analogous, getting either a graph frame or a data frame back from various algorithms you run. In terms of GraphX compatibility, we support pretty simple conversions between graph frames and GraphX. Say you have a graph frame, you can call GraphX to GraphX and immediately get a graph. Do note that the vertex and edge attributes are of type row, and that's in order to support non-long IDs in graph frames, where we need to maintain that data within the GraphX graph for mapping the original non-long IDs to the GraphX long IDs. You can also, with a simple function, convert back from GraphX. And if you do have existing GraphX code, I'd recommend checking out this belief propagation example. It basically has an algorithm implemented within GraphX using aggregate messages and then wrapped into a graph frame friendly API using these methods. Cool, so of course I should mention scalability. The current status is that the data frame based parts benefit from data frame scalability and performance optimizations like Catalyst, Project Tungsten, and so on. The GraphX wrappers, as I said before, are about as fast as GraphX plus some conversion cost. But there's work in progress, not just porting algorithms from GraphX to a data frame based implementation, but also GraphX has a few optimizations which are not yet ported to graph frames. So I'll give one slide on this, but also add a link at the bottom to a talk with a lot more info. I'll mention two of the ongoing optimizations. The first is join elimination. Basically, graph frame algorithms require a bunch of data frame joins, but not all of these are necessary depending on what you want to do with the results. So the solution is to recognize that vertex IDs serve as unique keys, and tracking these keys through the sequence of joins allows Catalyst, if you add a few rules, to eliminate some of the joins. The second set of optimizations, I'd say, are materialized views. And intuitively, I think of this as like data locality for common use cases. For example, message passing algorithms often need a triplet view where you have not just the edge data, but also the associated source and destination vertex data. So the solution here is to materialize specific views, sort of analogous to GraphX's replicated vertex view. But the real person working on these optimizations is this guy, Ankur Dave from UC Berkeley's AMP Lab. He gave a great talk at the Spark Summit East, which is linked here, where he gives a lot more info about these optimizations and also some cool benchmark results. As far as implementing new algorithms, there's sort of two methods. The first is to use data frame and graph frame operations. There are a few examples in the code if you do want to check it out in order to implement your own algorithm. Motif Finding is basically a series of data frame joins. Triangle counting has some data frame operations plus motif finding. And breadth first search is an iterative sequence of data frame joins and filters. The second method is message passing, using aggregate messages, which is the same primitive as in GraphX. For those who aren't familiar with it, basically it is a way of specifying algorithms by having vertices send messages to each other along edges and then aggregating messages incoming to each vertex. The interesting thing here, I think, is that we're able to specify messages and aggregation functions using data frame expressions. and even user-defined aggregation functions. So you can stay within the data frame and Catalyst framework. And there's some example code for belief propagation demoing this. Cool, so to wrap up, the current status is that it's published open source on GitHub. It's published as a Spark package as well, and it has releases compatible with 1.4 through 1.6. What I was demoing in was Databricks Community Edition, but it is also available in, and workable on other Spark distributions. There's good documentation with a number of examples for each algorithm, and I definitely recommend checking that out. I'd also ask that if you're interested, definitely contribute. We're tracking issues on GitHub right now, and I want to thank those who have already sent some pull requests. There will be links in the slides for resources for learning more. Not just the user guide and API docs, but also some of those have been translated to essentially executable notebooks. And there are also some blog posts, both introducing graph frames and also giving a much more detailed analysis of this flight delays data set. Thank you to Denny and Bill for helping with the demo notebook, and to Tem Shangri, Ankur, and several others now for graph frame development. And of course, thank you very much for listening. Cool. Questions? Sure. To GraphLab? Good question. I don't think there have been any benchmarks. I believe Ankur in his slides has some benchmarks against Neo4j and GraphX. But yeah, I don't think I've seen comparisons with GraphLab. Yeah. I think I saw a hand, and then you. Yeah.
What kind of scalability tests have you done with large graphs? What's the biggest graph you've tried?
So that's a good question. I have not really pushed it. I think the largest one that I have done was like 100 million vertices. But just as for GraphX, I think it also depends on the algorithm you're running. Some of the algorithms, are much more expensive than others. Yeah, that'd be great to like push it and be able to show numbers for each of them. Ankur at least has some numbers in his slides. Yeah, but. Right. So, right, with graph frames, essentially like you pass it data frames and it will keep things partitioned, basically using whatever Catalyst does. So, I mean, if you control any partitioning, like set the number of partitions on the data frames which you pass in, that'll certainly be maintained. But as you run operations, then control over that partitioning is really handled by, say, Spark SQL configurations.
You talked about querying in RDD for PageRank. My question is, what kind of interface there is between, say, a data frame and an RDD? And in your talk, you also mentioned Catalyst and Tungsten. Can you quickly mention in 1 minute how they work?
Okay, those sound like questions a little outside the scope of the talk, but there are definitely conversions between data frames and RDDs. There is pretty good documentation and examples online, so I definitely recommend checking that out. Catalyst and Tungsten are basically, the first is an optimizer, and the second is basically a set of improvements to the underlying implementation of data frames to do things like working off heap, trying to get a bit closer to bare metal speeds. And there is info online, but it's a very long discussion. Yeah, thanks. Other questions while get set up? Yeah. Why don't you go ahead?
How does this compare with Snap? We have to do GraphX and not Snap, Snap was network.
Right. I have to say, I actually haven't really worked with Snap myself, so I don't think I'm informed enough to give a good comparison. Yeah, that it would be good to just, if you're familiar with it, it'd be interesting to discuss offline. Yeah.
Any plans to support data sets?
Plans to support data sets. They're currently are definitely not in this release. In the future, that would be awesome. But I am not sure about like what that would look like. So I can't really say much about it yet, but I imagine that would be a good thing to do in the future. Yeah. Cool. All right, better switch over. Thanks a lot.
Thanks, Bradley. Joseph. Good evening, everyone. My name is Anand Iyer. I'm part of the product management team at Cloudera, which is the leading distribution of Hadoop and Spark. Today, we're going to talk about an open source Apache licensed project called Livy. And the simple one-line description of Livy is that it's a REST-based web service to interact with Spark. But first, a quick introduction. I've been part of the product management team at Cloudera for 1.5 years, and before that, I worked as a software developer at LinkedIn, where I worked on machine learning projects. I worked on feed relevance, so I've been on both sides. I've done a bunch of big data development, and now I'm on the project management side. So with that, let's dive in to Livy. Well, actually, before we dive into Livy, I should point out that I am not a committer of Apache Spark. And unfortunately, given that I'm in product management, I probably will never become a committer, but I hope that doesn't prompt you to walk out on me. All right, so first, let's look at the motivation for this project. The high-level motivation is to reduce the friction to use Spark, make it easy to use Spark, but maintain or retain its power and flexibility. And I will elaborate more by what I mean here. To understand better what the friction is in using Spark, let's look at the canonical recommended popular ways of leveraging Spark. First, we have Spark Submit, which is probably the most popular way in which Spark is leveraged. Spark Submit lets you fire and forget a Spark job. You fire and forget, the Spark job does a bunch of data processing and writes the results to some data store, probably HDFS, but it can write to other data stores as well. But the key thing is it's fire and forget. So it's not interactive, and that's the disadvantage of Spark Submit. Well, we do have the Spark shell, which is interactive, but even though it's interactive, it's rather primitive. It's a very basic command line shell. It's rather primitive. And yes, it's interactive. It's very useful when you're doing development of Spark jobs, but you can't really use it in production settings. And probably the third popular way of leveraging Spark is to look at it as a distributed database. So you have the JDBC, ODBC thrift server, and you submit SQL statements against it. So that's certainly a simple, convenient way of leveraging Spark. But SQL is not very expressive. It's limited in its expressiveness. Now, I realize that in this audience, we probably have a bunch of advanced users of Spark. And I realize that you guys probably are leveraging Spark in ways not covered in this slide. So quick show of hands if you are doing that, if you're leveraging Spark with some architecture that is not covered on this slide. Quick show of hands. All right, I'm quite surprised. It looks like these are the popular ways of leveraging Spark. Well, in that case, you should be interested in Livy because Livy opens up the horizon. It enables new ways of leveraging Spark. So the main goal here is to give you the simplicity and ease of use of SQL over JDBC. Now, SQL over JDBC has been around for decades, so it's rather passé at this point. But let's be honest, It's incredibly easy to use. Any client can just send over a snippet of some DSL, a little snippet, get a bunch of complex data processing done on the data processing layer, and get back results. And the simplicity of this paradigm has enabled almost all the applications that we use today. So it's a very important paradigm. And we want to bring this simplicity to Apache Spark, but still leverage the full expressiveness and flexibility of the language or the API that Spark provides. Now, if SQL was enough, if SQL was all you needed to express your data computation, we wouldn't have complex programming languages like Scala. We wouldn't have Apache Spark with its flexible expressive API. So our goal here is to give you that full flexibility and expressiveness with the ease of use of JDBC over SQL. That'll open up whole new ways of leveraging Spark. It'll open up a whole new set of architectures, and it'll open up Spark to new use cases, and that's what we're aspiring to. But let's not forget, as you open up Spark to new use cases, you still want to maintain the enterprise-grade features, such as security, comprehensive fault tolerance, and so on. And that's also a key goal of the Livy project. So what is Livy? If I were to give you if Livy were an entry in the dictionary, the one-line description of Livy would be, it's a REST web service that lets you manage long-running Spark contexts on the cluster. What does that mean? Let's look at the architecture, and that'll make things clearer. So here, that rectangle in blue represents the Livy web service. You have multiple independent clients that are talking to multiple independent Spark contexts through the Livy REST server that acts as a proxy layer. The key thing here is that Spark itself, the Spark contexts, and the different executors are running on a robust resource management layer, such as Yarn or Mesos. Each context can be configured differently. Each context can have different number of executors, different parameters, and so on. They're completely independent, and you can have multiple clients that can talk through Livy to the same context or different contexts. The clients can submit jobs, get back results, and so on and so forth. So that, at a high level, is the architecture of Livy. So on the subsequent slides, I'll talk about why this architecture is compelling and important. I'll first cover the architecture and then talk about the API and how the API opens up new ways of leveraging Spark. So let's look at why this architecture is important. It provides good fault tolerance, and I'll demonstrate that with an example. Each Spark context here is completely independent. So let's just say the Spark context marked by the X happens to go down. This is cluster compute, machines fail, processes crash. Spark context will go down. So let's just say that one goes down. Now, because it's running, let's just take the example of Yarn. Because it was running on a Yarn cluster, Yarn will restart that driver, the Spark driver, restart that context. And the client can simply reconnect to that context. So the client honestly may not even know that the context went down, or the client may see that the context was temporarily down, but then the resource management layer restarts it, the context reconnects, and things are good to go. That fault tolerance aspect is very critical. One Spark context failing does not affect other Spark contexts. So that's very robust. You can have, depending on the size of your cluster, multiple independent Spark contexts running simultaneously. Now let's look at another case where fault tolerance is important. Let's say the Livy REST server itself goes down. I mean, it is software goes down. Well, it has high availability features. It comes back up, and then the clients merely continue talking to the contexts that they were previously talking to. So as you can see, Livy enables a very robust architecture of talking to different contexts, controlling those contexts, and having contexts that do not step on each other's toes. And that's important in an enterprise setting. Now let's look at another important enterprise feature, security and user impersonation. So with Livy, clients can authenticate themselves as a specific user, and then start up contexts that run as that specific user. So each context, the jobs that are run on that context, they only have access to the data sets that the client that started the context has access to. So now you can have multiple independent contexts running as different users, and each context only has access to the appropriate data. That's another very critical feature for proper, robust enterprise readiness. And again, the Livy architecture enables that. So now let's look at the API. Yeah, quick question.
You mentioned earlier that client A could get access to client B, they could get access to the same context.
That is correct. They can talk to the same context as well.
That is a privilege, I mean, that is not on each other.
No, well, at that point, the contexts, the different clients realize that they are talking to the same context. So it's multiple clients submitting jobs, and of course, the context has to be configured with the requisite amount of resources. So it is a flexible architecture. And just like JDBC over SQL, where you can have hundreds of simultaneous JDBC requests going to an underpowered database and overpower the database, similarly, this architecture is not foolproof. You can certainly overpower the context and bring it down. That's certainly true. So it's a flexible architecture, but it's not completely foolproof. And I go back to that JDBC analogy. It's very similar to that JDBC analogy. So with that, let's look at the API. And the architecture is fantastic. You know, it's great, but at the end of the day, the developers are using the API that's available. Now, I should call out that this is a very nascent project, so the API is going to undergo a lot of change. So what I'm describing on this slide may not even hold true. The subtle aspects of it may not even hold true a month or two from now. So the first API use case is just simple jar submission over REST. This is just a wrapper for Spark Submit. So it's basic Spark Submit over REST. You provide a jar, and then you provide the same set of parameters that you provide to Spark Submit. So it's not terribly interesting, admittedly so. But the advantage here is to submit your Spark job, you didn't have to log on to some edge node which has Spark installed. Doing it over REST, you just talk to a service, does simplify the whole process. But still, admittedly, not terribly interesting. The reason it's not interesting is it doesn't let you pull back results of your Spark jobs. For that, we have another API that enables fine-grained programmatic job submission and result retrieval. You essentially get a thin Java client which will handle the serialization and deserialization of data. It'll submit your job, it'll get back deserialized results and deserialize it for you. And this simple Java client can now enable use of Spark as a data backend for multiple application tiers, mobile applications or web applications, similar to how mobile or web applications leverage JDBC to talk to databases. So let's look at an example to make this more concrete. So in this example, the first thing you're doing is creating an instance of the client. When the instance is created, you specify a bunch of parameters, you specify the context that it's connecting to, and so on and so forth. In the next line, you submit an instance of your job. And we'll look at what your job is. But your job essentially has the logic that you want to run on the Spark cluster. Then on the third line, you're waiting to get results. You have synchronous and asynchronous APIs to get results. You have a synchronous API where you block till the results come back, or you have an asynchronous API where you can poll to get results. So that's the simplicity of using this client API. So of course, the critical thing is what goes into that your job instance. So to define your job, you essentially extend this interface called the job interface, which can be parameterized with different types. It has a callback function called call, which gets as arguments an object called the job context object, which has the various Spark contexts or SQL contexts, or if it's a streaming job, it can have the streaming context in it. So essentially, now within your call function, you can embed any Spark logic. You can take the logic in any Spark application that you might have today and embed it here, because essentially all you need is access to the various Spark contexts, which you do get in this callback function. So essentially, in this callback function, you get the full power and flexibility of Spark. You define Spark applications, which are a directed acyclic graph of transformations, and that directed acyclic graph culminates in an action. So in that last line, we invoke the action, which gives you a set of results. Those results get serialized and sent back to the client. Let's just review that with an architecture diagram. So essentially, you have clients that are sending serialized closures over Livy to a specific Spark context. On the Spark context, that job is executed just like any other Spark job. Results are taken from the action, serialized, and sent back to the client. And I hope you'll agree this opens up whole new ways of leveraging Spark. Just nod and humor me. This is fairly compelling, and even if you don't see that now, I'm sure this will sink in, and this really does open up a whole new paradigm of leveraging Spark, which is currently not possible today. Yeah?
Is the job context executed any time during the execution of the job, or is it
That's a good question. So the Apache Spark itself, the Spark context can be configured to deal with jobs in different ways. It can be configured to have jobs go into a queue where it does one job at a time, or it can be configured to process a bunch of jobs simultaneously. Because at the end of the day, the Spark context processes your job, converts the DAG, breaks it up into tasks, and then it's doing scheduling of the tasks on the executors. So you actually get to configure whether it does each job sequentially, or if it does multiple jobs in parallel. But of course, as soon as it receives a job, it goes into that queue and it's going to get processed. I hope that answered the question.
So the result, is it possible to be an RDD?
Oh, so it can be an RDD, it can be a data frame, it can be a streaming job. It doesn't matter because you get access to the essential Spark contexts or SQL contexts or Hive context or streaming context, which is what you need to create RDDs or data frames or so on.
So the RDD will go back to the client?
The RDD itself will not. So any Spark application culminates in an action where the result of an action is not an RDD. The result of an action is either like one double or list or whatever. It's a set of JVM objects. Those go back to the client. The RDD itself does not. It's the result of the action that goes back to the client.
But it can be a huge list, and trying to convey that.
Absolutely. And that's a valid point. And it's not a new problem. When you do JDBC over SQL, it's the same issue. The result of a SQL statement can be a ginormous list. So absolutely, again, this is a flexible API, but it's not foolproof.
I don't understand the wisdom of having an API on top of Spark. For example, to address what you said, I never saw the wisdom of trying to do JDBC with SQL or whatever you're talking about. I mean, when you need to do programming, SQL is not appropriate. So similarly, if you want to do a combination, you would rather do it in Spark. Why would you expose it to remaining to using an API?
No, that's a very valid question. So we have customers. There have been instances where people want to create what I call pseudo-interactive applications, where you have someone log into a web application, pull a bunch of data sets, do some processing on those data sets. That processing cannot be expressed via SQL. It's complex processing. It could be graph processing, for example, which cannot be expressed via SQL. But it's pseudo-interactive. They want to submit that job, and they want to see the results back in a few minutes, or if the data sets are small, in a few seconds. This enables them, through that web interface, create their job, submit it, get back results within a matter of seconds, and view them, which is not possible with the other paradigms. That's why this is compelling.
So, I think it's a valid additional way to get your hands on the Spark.
Oh, absolutely. Spark is the king. This is just opening up a new path to Spark. We have a skeptic here. Totally valid to be skeptical. Can you repeat the question? I didn't catch that. So good question. So fundamentally, the definition of an RDD is data that's distributed across the executor node. So an RDD is never held on the driver itself. An RDD is a distributed data set held on the executor. So by the fundamental definition of an RDD, it doesn't make sense to return an RDD. And also, this is just piggybacking on the way Spark is defined. The way Spark is defined, the driver node uses RDDs to get a bunch of data processed. Every Spark application culminates in an action, which is not an RDD. It's a set of results that go back on that driver node. So by the fundamental definition of an RDD, it wouldn't make sense to return the RDD itself. You do want to invoke an action. We can do more questions, but let's go through the whole presentation, and we can come back for questions. So the third case is for people who are incredibly lazy. They don't even want to use the Java client. Now, I'm being facetious here. So the third case is you just get to submit over REST textual snippets of code. It's just a little blob of text that has your snippet of code. And Livy has interpreters, which is very similar to the Spark shell, for example, which will interpret your snippet of code, produce the results, and send them back. And this particular API use case is to power interactive notebooks. So Joseph did demonstrate one interactive notebook. There are multiple other interactive notebook solutions out there that want to leverage Spark. And in an interactive notebook, you're essentially typing out a snippet of code. And then when you hit the run button, that snippet of code is sent over to the data processing layer. It processes the data and sends results back. And that's what the third API enables, sending snippets of code that are interpreted, and the results are sent back. And yeah, so this is just sending a snippet over REST, getting back the results over REST. And we actually have an example. We have a running example. We have a Jupyter Spark Magic. So actually, before I talk about the Jupyter Spark Magic, quick show of hands, how many folks are familiar with Jupyter or have used Jupyter notebooks? All right, that's quite a good chunk of people. Awesome. So Jupyter is a popular notebook solution, and the Jupyter community has wanted to leverage Spark as a data processing backend. There are actually quite a few solutions out there. With Livy, there's one solution where you embed what is called a Spark Magic into your Jupyter notebook that contains your snippet of Spark code. It sends that snippet to Livy, gets back results, and that Spark Magic for Jupyter also has a bunch of visualizations. So you can get back the results and then visualize them as a histogram, as a pie chart, and so on and so forth. So this enables a very rich interactive REPL use case. It's not just basic command line. You're submitting snippets of code, getting them executed, getting back results, visualizing them, and so on. It's very similar to what Joseph has already demonstrated. So Livy powers this rich notebook experience, and Livy can become a backend to the various notebook solutions out there. And that's why Livy is fairly compelling. So this particular Jupyter integration has been authored by our friends at Microsoft. So there's Jupyter Spark Magic and some work within Livy itself to enable this solution has been done by Microsoft. They've been contributing to Livy for months at this point. Actually, before I talk about future work, I do want to emphasize that this is an Apache licensed open source project. We want to grow a very vibrant community. We are, and I'm biased here, but I like to believe, breaking new ground in opening up ways to leverage Spark. Certainly, we're going to stumble along the way. We want a wide community to better understand what makes sense. We want to grow the community, so please do contribute. Check out these links. It's an Apache licensed open source project. We definitely want to have a vibrant community. We have folks from multiple different organizations contributing to it right now, Cloudera, Intel, Microsoft, and so forth. Quick question? To be announced, but that's orthogonal. It's an open source project that's available to everyone. So yes, it's likely it becomes a part of the distribution. It's also likely we submit it as to the Apache ASF incubator. But those things are to be discussed. Key thing is it's open source, and we want to have a vibrant community around it. So with that, let's look at some of the roadmap items, what's coming in the future. So the first thing is to actually release a stable version of Livy. It's a very nascent project. It's very nascent, started towards the latter half of 2015. We hope to release a more stable version in about a month or so. After that, the goal would be, first goal is to get security done. Secure access to Spark, which enables usage in enterprise settings. Then we want to add high availability, proper high availability, where when the server goes down or contexts go down, they come back up, and you essentially resume where you left off. And then we want to simplify the API to make it easy to share RDDs or data frames between different clients. So fundamentally, the architecture enables that, but we haven't opened that up in the client right now. So different clients want to share the same RDD, which is very natural, especially if these RDDs are cached in memory. Different clients want to run jobs on the same RDDs. We want to make it easier. We want to enable that in a simpler way in the client, which right now is not possible. So that's on the roadmap. Yeah.
Are you looking at any other security plugins besides Kerberos?
We have Spinego security integration. And this is a community project, so the community drives what's required. But at the moment, yeah, Spinego and Kerberos are on the roadmap.
So more of a plugin architecture, different security patterns. Okay. Same with the currently aren't the only cluster management support, or do you have interest in
So, so Spark standalone currently doesn't work with Livy, but you could make Spark standalone work with Livy as well.
So, just to directly answer that question, there's very little thing that's Livy does specifically that's more specific, that it needs to like enhancement of the ability to handle back on the application. So, with Macy's interaction, a way to get handled like there where the end of the running. So Livy itself doesn't need it. It's a matter of like having that ability to right, so all these drivers are running like in the cluster. The drivers aren't actually running on these commands. The drivers are running. The drivers are running line code in the cluster, so they're all cluster. They're applying to the driver. Yeah. Okay.
So Livy, do you run them in additional, or you run Livy?
You'd have to, Livy would run on the edge node as part of the cluster. So ladies and gentlemen, that's Costa Sekelis. He's the engineering manager working on Livy. So he actually makes code contributions to Livy. Not yet? Okay.
I have a question for you.
Yeah.
Anybody providing a hosted solution for Livy?
Um,
Selling Livy as API service?
So the question was, is anyone providing a hosted solution? So Microsoft is working on Livy because they plan on leveraging Livy as part of their hosted solution on Azure.
Nobody right now.
Actually, they might already, I don't think they're live. They'll go live fairly soon. Yeah. Question? The question is, have we done any performance measurements? No, we have not benchmarked it, but there's no reason to believe it'll run slower than any Spark job. It's just Spark. So there's a subtle overhead. We haven't done performance benchmarks. Yeah. That's a good question. The question is, do we limit the result set size? At the moment, we don't. So you could, in theory, ask for a ginormous result set, and I'm not sure what will happen at that point. So we haven't added those limits, but it's likely we may add some sensible limits to how big the results can be.
Yeah, and have you played with the snippets, and how complex can be the snippets?
Oh, the snippets can be arbitrary Spark code. there's no limit to the complexity of the snippets per se. They can be arbitrary Spark code. Actually, I agree. So the fact that it can do arbitrary snippets might seem too good to be true, but perhaps we should look at the Spark shell as an example. Whatever snippets the Spark shell can process, the same snippets can be processed here. So I think, and correct me if I'm wrong, internally it is using some of the Spark shell code to process those snippets. So, yeah. Right. So anything you can. So anything you can run in the Spark shell, you can run through Livy as a snippet of code. Yeah.
Support for Spark streaming, and then does it support the model of Spark streaming and being able to regularly query the new results?
That is a good question. So in theory, it does. We just haven't gotten around to testing that. So in theory, nothing prevents that, but we haven't tested that yet.
The second question had to do with your demonstration of Jupyter integration. Jupyter has an existing protocol for talking to a processing engine via the IPython kernel protocol. Is there any reason that you decided to step up a whole new mechanism for remotely communicating to a processing node and not use the existing IPython protocol?
That's a good question. The question is, why not leverage the IPython protocol that is already in place? It has certain limitations, especially when you're talking about integration with other systems and security and so on, which gets simplified with a REST-based interface. That is a bit of a longer conversation. But the long story short is, it had certain limitations for the types of use cases that we wanted to enable. Yeah. That's a good question. So the question is, how is it different from the Spark job server? There are two differences. The first difference is architectural. The Spark job server doesn't run the Spark drivers. On the cluster manager, it actually runs the Spark drivers within the server. Which actually becomes a single point of failure. And the other differences are more subtle. They're API differences. Awesome. Great. Thank you, folks, for attending.